I looked up to the government.
So I thought what we'd start with is why don't you ask each other a question? We probably have the same questions. Mary Lou, why don't you ask, do you have a question for Ben?
Sure, I loved the presentation. I have a lot of questions. It's fascinating. Those lifetime is 2 years, and you can get the tissue, but you don't need to scan it. So that's super cool, right? So where do you put it in the tissue?
Yeah, it's a great question, and so the science of the sensor is that it measures its immediate surrounding.
Right.
So the answer is not driven by the platform. We know what it does. The answer actually is driven by the physiology. What is it? What's the information that you're trying to get? So for systemic disorders such as diabetes, for example, yeah, it's distributed, right? So two things, you could put it anywhere.
Is it about the size of a rice?
It's
grain
tiny.
or-
No,
Oh, it's
rice
even
is
smaller, that's right.
yeah, rice is actually bigger than that. Yeah, this is when I had it injected in me. I mean, I'm a little bit afraid of needles, right? But it just wasn't. It's like getting a shot, right? It's like getting a shot. So it depends on the application. For the wound care application, for example, you put it right next to the wound because what you worry about is the local environment, and you want to see the local environment recovery.
So the oxygenation there.
That's right. But for applications such as diabetes or COPD, you put it around the core because it is a physiological response, and since the body's glucose level, for example, is kind of prevalent everywhere and it's pretty uniform, and the lag time of glucose calibration within the body is within minutes. It's over the range of minutes. It really doesn't matter where you put it. You're going to get the right information.
It's fantastic. Can we put more of the material inside of this?
You can. You can. So
where's the?
yeah. So where's the well, I tell you
you want to know what's happening everywhere, right?
You could. Well, the potential application here is actually pretty neat. When you kind of think about, you could map out a variety of sort of distributed biomarkers around the body. The material is so small, and the foreign material that we put inside the body is actually so it's just negligible that the amount of sensors you put inside the body is actually not a.
And what's the response time?
It's
just
very,
connecting neurons?
Yeah, it's very, very fast. One of the things that we actually have toyed around, so we've been fortunate to have gotten funding support from NIH and also from DARPA. One of the things that we're talking about with DARPA is using these sensors as sheets of neuromuscular junctions and look at electroceuticals, right? So electroceutical is this field where neuron firing and the frequency of neuron firing is used to control organ function, and therefore as a therapeutic for certain diseases. So you're not putting small molecules inside, you're just kind of using the body and fire the neurons in a different way.
So you can get into milliseconds.
Yeah, yeah.
That's awesome.
The fluorescence lifetime decay here is in the order of nanoseconds.
Wonderful.
Microsecond decay is on phosphorescence, so one of our detection methodology is in that range. So milliseconds is
such a cool material and system. It's fantastic.
Yeah, thanks.
I'm very excited about it.
By the way, say hi to Slava. He helped develop this.
So when can we try it? When
He's
can we
actually an
try
organic
it?
chemist, company.
Oh, in a different country. It's
Yeah,
the US
so-
is not known for the most
No, we
innovation
actually-
in healthcare, right?
We actually have a couple of studies going on in the U.S., and we're about to kick off a few more studies in the U.S. to get our first FDA approval next year. So stay tuned, and there are a lot more exciting things coming out of what we do. But there's only a certain finite number of hours in the day that we wake up and try to contribute to the world. So we're really feel fortunate that we could do this.
So Ben, do you have any questions for Mary Lou?
Yeah. So at what age did you realize you were brilliant?
I haven't gotten there yet. So, but you were.
No. All kidding aside, I think the first time I met you, you had just started Openwater, and you were just describing the concept a couple years ago. You were just describing. It was either at Fortune Brainstorm.
Oh, that would
right?
be, that's right.
That's right, and that's the first time you actually got on stage. You were talking about it. I was just intrigued by it. Congratulations on the progress that you actually made. Listen, what's like? I want this to happen so badly myself. What's the remaining risk? What you've come so far. There's so much that it's been accomplished. is there any technical risk left? And if so, what is it?
The biggest risk we face now is the cost of the laser in the near term. We've got 2 laser paths, one's a little bit expensive, and in the long term, we think we can reduce it. So we've gotten, I think, out of the technical risk, but the laser we're making became more and more complicated. And so now we've made system changes to make the laser easier. It had to be a very, very fine color or wavelength bandwidth, for those of you that speak in that, and pulse in about a microsecond. And that's because we record holograms of your body,
Right.
which is how we get the resolution
Right.
in a different way using these camera chips. But here's the thing is, we're alive, it's good to be alive, but that means we move.
Right.
And what your body does is scatter this red light. And we need to record the hologram before the scattering happens too much. That's the moving of the white blood cells, for example, through your body. And so for that, we've got about 10 microseconds. And so we've actually been figuring out ways to dramatically change that to enable a dollar laser. But right now, the laser's more expensive. So that's really what keeps me up at night.
Yeah.
The other thing that keeps me up at night is I suppose just normal stuff for management is we've got great people in our team, and I need it to be a great team too. It's
Yeah.
good.
Yeah.
You haven't lost anybody, everybody's happy, but like, you know, we're growing, and it's just their standard startup stuff,
Right.
I suppose. Then FDA is a little bit scary, but the predicate products for near infrared light, as you know, go back 100 years. We know the safety levels, and then ultrasound. Most pregnant women in the developing world have had ultrasounds for the last 50 years. So there's all these predicate products for safety. And so, yeah, I suppose the third thing that keeps me up at night, and maybe for you too, we're a hardware company. Death to a hardware company is picking the wrong first product because it's expensive to develop. And so again, we're not pitching, I think we're just trying, you probably either, it's like there's so much investment to the hardware, you want to make sure, like you, I think we want to make our first product to be the thing that can provide the most good to humanity. And just, you know, do we do breast imaging, do we do liver, do we do the ambulance for the what kind of stroke? Because it's the end-to-end thing. Like, how's the nurse gonna use it? How's the insurance gonna read it? Like, all of that is super
Absolutely.
important for that to be able to be delivered to people, which is why we're probably both here talking about it, because we wanna know what's gonna kill us beforehand.
Absolutely, absolutely. And I think at the end of the day too, what's unique about healthcare, and by the way, we celebrate it, it's not a complaint, but the regulatory scrutiny is so high, and rightfully so, right? You know, as an innovator, you're bugged by it, but as a parent, you celebrate it. You say, "Oh, that's great." I love the fact that the FDA exists, because every time my son goes to a hospital, I don't have to worry like I do when I was in China. You kind of worry, you know, at the hospital, like, where did that vaccine come from? Who made it? And whereas in the U.S. you don't, so you suffer. But as an innovator, it's tough, and it creates this even higher burden, to your point of gotta make sure you're right the first time out, because that journey is so long and so expensive that you can't fail fast.
Okay, we have quite a few questions, some pretty technical, but I think if we could spend like this might not be possible, but somewhere around a minute on each question, I think we can get to most of them. The first one's probably easy. Mary Lou, why the name Openwater?
This rock star human rights activist, Pierre Gabriel, called me almost, it felt like every week, it probably wasn't that much, trying to convince me to do this work outside of Facebook. And he wrote an essay for The Edge, something in the news lately, John Brockman's organization. He wrote an essay about, who I have nothing to do with, just for the record. He wrote an essay about our thoughts flowing like water, and needing to have swimming lessons to learn how to deal with this coming online. And so literally was joining the board of a public company and never wanted to fill out the SEC paperwork again for conflicts of interest. And so I wrote to Peter like, hey, can I use the name and incorporate it? He said, sure. And so I used the name to incorporate it, and it's just stuck. So
Okay, there we go.
that's it.
So, this, Mary Lou, this one's for you. Mary Lou, suicide is the second leading cause of death in California among 10 to 34-year-olds. What system or systems are you building to be part of the solution, not the problem? Mental health conditions are the highest spend in the country, over 200 billion. So she just...
Yes.
Okay.
Yes, absolutely. So the problem is you have to move the whole field of psychiatry out of DSM and the subjective measure to an objective measure, and then start to develop it, and it takes time. And I know the house is on fire. It's awful. Clinical depression, on average, something like 20% of us will get it here. If you lived in a war zone, your chances go up by double, and you lose 12 years of your career. It's awful, and what we have is not working very well, and the drugs have not changed significantly in decades. It's a huge, huge problem. Where I go for us to be successful as a company is we're probably better at finding breast cancer and liver disease first, or what kind of stroke you had. As we prove that, as we get these systems to psychiatrists to start proving where they can be useful. So we want to get these systems out to more people, even though we think to prove how we can reduce, for example, clinical depression may take some years. So,
Okay.
but we care.
Okay. Dr. Wayne, how will this, okay, so, I'm sorry, there's two parts. For Openwater, Dr. Jepsen, what will the regulatory challenges be? How will a big data approach change diagnosis? And then how will this change the,
The concept of normal physiology.
concept is the word, there we go, so sorry. Concept of normal biochemistry.
Can he go first? He hasn't spoken in a
Yes.
while.
Oh, sure. That's the first time anybody said that to me in my life. I haven't spoken in a while. For those of you who work with me, you'll know what I mean. Notice Slava's laughing. That's actually the one of the most exciting things that we look forward to is if you go get your blood drawn today and you get your values back, you'll notice this range of healthy, right? You'll come back and say your hemoglobin level, and this is the healthy range. And sometimes the range is pretty wide, and you'll see this bracket depending on how the report is written, and you get this X right here in the bracket or outside of the bracket, and you say, okay, I'm reasonably healthy. The thing is, we're all incredibly different from each other, right? She's 1,000 times smarter than you. You're 10 times more handsome than her, right? You could jump higher, you could run farther, etc. We're different, and thank goodness for that. But what that also means is our biochemistry inherently has to be different. How we manage recovery from the deviation of the norm is different. A very personal example, I have a history of gout in my family. So my uric acid level in my family is really, really high. My resting uric acid level is probably about 12 mg per deciliter. If you're at 6, doctors put you on allopurinol, right? Less than 6, you are kind of in the normal range. I'm at 12, and that's jump around between 10 and 12. Listen, it drives my doctor crazy, but that's just kind of who I am, and I'm abnormal in that sense. So I would hypothesize what happens is, if you could look at your biochemistry over time, and you could look at the deviation from that for you as an individual, and then how quickly and how it recovers down to quote unquote normal, what your baseline is. Over time, what you're gonna be defining for you is a normal for you, for yourself, that you're not normal relative to everybody else. You're normal relative to when you feel the best, when you're healthiest. And I think that's a wonderful outcome for all of us.
Is it also taking medicine back to being the patient rather than the numbers?
Exactly, absolutely. My gout is a goofy, simple, but real example of that, right? My doctor is trying really hard to get my uric acid level down to 6, so I'm on allopurinol. Listen, is that necessary? Probably not. and yet it's a source of potential waste for the healthcare system, because my therapy is being calibrated against a broad population that's very, very different than me. Now, by the way, that's the only way that it could be done today, so hooray for that. But I think this refinement of who we are over time, longitudinally, is kind of the way of the future.
Okay, and here's a question for probably both of you. What about data security? Are there concerns about that and personal privacy? How does the doctor interpret the data, especially a PCP? I'm sorry, PCP. Primary care physician,
Yeah.
sorry. Yeah, so, go back.
You go first.
Security, yes, we care enormously about it, because the system that can see inside of our body can see inside of our brain. And where this goes in the limit, like Mars, first thing medical imaging, but where this goes is that last bastion of privacy, thought. Even though it might be grainy at first, even though it might have 5% false negatives, we still care deeply about that. And so we've created systems like a tokenizer ring and so forth is what we're working on to assure. You might want some people, your spouse, some of your friends, your kids to have information about you, but not everybody. And there might be these rings. And to answer the other questions about regulatory, we're using near infrared light and ultrasound at levels that have well-established safety levels. The next thing is that we make an image. Is the image repeatable? And from that, you would then infer claims of, that's a clogged heart, that's a cancer. Or you care about the answer in the terms of data of collection, much like you, like 3 questions for tumors. 30% of us are gonna die of cancer statistically, another 30% heart disease, like that's 60% of us. You know, is it getting bigger? Is it getting smaller? Is it staying the same size? How does that change over time? How does your diet affect it? Wow, maybe you can start to modify based on that cheesecake last night or the salad, or maybe for me, the cheesecake's better, you know, that would be lovely.
You know, the data side is something that we obviously pay a ton of attention to, because ultimately what we do is just unleash, both of us, right, unleash a huge amount of data that didn't exist in the past into the world. Before I go on to my soliloquy about data, let me just right off the bat saying, you own your data.
Right.
We fundamentally believe that you own your data. It's your data, it's nobody else's business. It's not mine, it's not Profusa's, it's yours. That's the starting point. Now that said, here's my soliloquy.
A 30-second soliloquy,
Absolutely.
please.
I used to not think that I would want everybody to know my every thought. I used to not think that I would want my credit card to be all over the internet, credit card number. I used to not think that I would want my vacation schedule and what my kids look like to be posted so everybody actually could see it if they want to. Fact is, I think the way we think about data and feel about data changes depending on what benefit you feel like you're getting back from it. And from our perspective is you own your data, but I think what's going to happen is right now all of your healthcare data is controlled by the physician in the hospital, right? They're the source of your biochemistry data. You go to the lab has it. You don't get to see it first before your doctor sees it. When you have technology like ours starting to be embedded into your life, you control that data because the source of the data is from you, is from your instruments, from your phone, is from your device. And the physician in the hospital has to ask permission to get at it. It doesn't start at the hospital. It doesn't start at
Which
the
is why we'd like to go consumer,
exactly.
for that reason, otherwise the
And that's-
hospital.
That's right. And I think that changes it changes the tidal wave of how people think about data. And if you have control over it, then you get to define what benefit you get out of that data and how much it costs and what it's worth to give it up. And then it becomes your choice.
Okay. Ben,
I'm sorry,
this
that was a minute.
That's okay. This one has to be, less for sure. This is also for you. When would the system be accurate enough to be used as a continuous glucose monitor?
Give us 18 more months.
Okay, ooh, I like that one. That was 10 seconds,
Yeah.
5 seconds.
5.
Okay. Let's see, 2 points here. It doesn't say to who. Analogy of pacemakers with home monitoring. That's number 1. They want it. And then are companies public? I'm
I'm a private
not sure
company.
what exactly.
We're private venture-backed
Right,
company
right.
as
Yeah.
well. We don't have a
Analogy of
product.
pacemaker with home monitoring. So I guess the question is,
Well, just
Yeah.
an analogy, the real-time thing, I have a pacemaker and I have this thing beside my
That's
bed.
right.
And so I have the real-time monitoring of that particular part of my data. And that's an analogy to what you're gonna do on a much larger scale.
That's exactly right. And by the way, that pacemaker, it's not like a nurse. By the way, all this data, one of the things that healthcare systems might push back on is, I'm already so busy as a physician, I don't need all this data coming in my face and what to do with it. Point though is, our Nest camera at home, it pings me only when something happens above a threshold that I set, right? And the rest of the time, the camera's doing its thing, but I'm not getting bothered by it. And it'll be an analogous case. Yeah.
Okay, we have 4 more questions. I don't know if we're gonna get to all of them, but we'll try here. And I'm gonna try to read this accurately. What's the largest molecule you can read, e.g. can you detect peptides or nucleotides? And then the next word I cannot read, IMM, I don't know, or liquid biopsy.
Immunoglobulins, yeah.
Oh,
No?
do you need to worry about signal, anyway. Yeah. We should have a typewriter in here.
Oh, amplification and signal to noise ratio. Did I read that right?
Yeah, that's right.
Yeah. The size of the molecule is of less importance. What's important is the compartment in the body that we read is in the interstitial fluid space. So we can't count red blood cells, for example, because that's inside the vessels, capillary. We're outside. We're in the fluid that bathes the cells. So any molecule that's available in that space, in theory, can be detected by our methodology. Depending on what you're measuring, you may need signal amplification. But what's actually probably more significant is if the molecule that you're measuring is in such low abundance, your sensor may not be reversible. But then it's okay, it may just be a surveillance sensor, right? You may just be around, it's like, okay, once it detects something and it binds onto it, it'll never let go. Then you have to put another one in. There's certain markers from cardiac cells as a precursor for heart attack, for example. HIV detection, surveillance, right? Those antibodies are in very low abundance. You can have a surveillance sensor in that sense, because when it's low abundance, you have to have the binding constant to be so tight that it won't let go, and you just won't be at physiological level. But as long as it's in the interstitial fluid, in theory, we can make it.
I think we can get to all of these. I'm hoping this next one isn't too long. If Mary, Lou, it's for you. Are the camera chips you use RGB/D chips? How does ultrasound interact with near IR light to produce image?
When we put a focused ultrasonic ping in the body and illuminate at the same time, the light that passes through the focus changes color ever so slightly, just like the pitch of a police car siren. Physically changes as it goes by you. It's called Doppler shift. That's the technical term. And so we employ that by shifting another beam of light by that amount of color, and then beating that on a camera chip to record a hologram. But we make our own special chips. There's chips in cameras, but they're flawed in different ways, in cell phones and so forth. But we make our own camera systems that don't use the red, green, and blue pieces of Jell-O over the filters that enable us to have beautiful pictures of ourselves and our selfies and so forth. And so those are removed and have a very high conversion efficiency photon to electrons, because cameras take light and move it to electrons, so an electric signal, but with very high efficiency in the near infrared. So we use those, and the fact that the pixels are the size of the wavelength of light, so we can record the waves and the wavelength of light and how they beat together, which gives us much more information. And we don't get just the intensity of light, we're able to capture the phase of light, which is what's giving us this extraordinary resolution and image quality.
Wonderful. 2 more questions. How might our MRI detect seizures, epilepsy?
Yeah, we could detect, you could put it in your pillow, you can put it in a ski hat, and so you can detect seizures or pre-seizures in such a system in the future. Again, we're probably starting with heart disease and cancer, but maybe we should accelerate. So there's some organizations trying to get us to accelerate to the head. I think that might be super important in ambulances as well. And so how can we bring on more functionality? Back to the regulatory question, when you get FDA, the details are first you prove it's safe, actually that's CE, then you prove it does something, you have a claim like it makes an image, it's a repeatable image. If you try to say that image is an epileptic seizure, you need to prove that, so that's called a clinical trial. If you just say that's an image, and you take lots of images, you can say, boy, that lump's getting bigger in my breast, it's getting smaller, and the inference of that is a faster road, we think, than perhaps the other. We're doing it all, but we're trying to phase it so that we can provide value sooner.
And the last question, and then I need to close the program out. You can each answer this. It's a great last question. How does one gain access to these technologies?
Implants at the door?
Yeah. My email address is ben@profusa.com. No, if you're in Europe, the technology actually, as I mentioned, is CE approved. We have clinical studies that are ongoing. I can't recruit you, but you could volunteer. So.
Okay. We'll have alpha kits at the end of this year, and we'll probably support a few organizations, beta kits next year, which will be more widely available product thereafter.
Okay. So I think we would all like to give a big round of applause to So thank you for your comments here today. We also thank our audience here as well as those listening to the recording. And now this meeting of the Commonwealth Club of California commemorating its 114th year of enlightened discussion is adjourned.